In the lab this week, we'll be talking about how to determine the possible directions of acceleration for a two-dimensional motion. In a one-dimensional motion, it's pretty easy, but in a two-dimensional motion, it's more complicated. And the reason for that is in a one-dimensional motion, remember, acceleration means that the speed is changing. It's either getting faster or getting slower. But with two-dimensional motion, there's a new thing that doesn't occur in 1D. So acceleration means first the speed can be changing. But besides that, you also have acceleration if the object is changing direction, if the object is turning. Okay. In one dimension, there's no such thing as turning because you're just staying along a straight line. But in 2D, we have to think about this. So the first thing in this lab that you need to do are a few problems that are trying to make the distinction for one-dimensional motion. So in 1D, you can think of there being sort of two different ways that you can represent an object's motion. So two types of representations of motion. The first one is a position versus time graph. And then the second one is a picture that shows the path of the object. And then on top of that, you'll have a velocity and an acceleration vector drawn. And it's very important that you make a distinction between these two things. When we go to two dimensions, the only thing we're going to have are these paths of the object with velocity and acceleration vectors drawn on. We're never going to have position versus time graphs anymore. But the path of an object in 2D can look, like a position versus time graph in 1D. So the first thing that you always have to do when you see a picture that represents a motion is you have to know, am I looking at a position versus time graph for one dimension or a path with a velocity and acceleration, which can be in one or two dimensions? Okay, so let me do an example that's similar to the first few problems that you'll have to do. So let's say that a ball is thrown straight down towards the ground. Okay, and we want to do two things. First, we want to draw a position versus time graph of that motion. And second, we want to sketch the path of the ball and at a single location along that path, that represents a single instant. So at one instant, we want to draw the direction of the velocity vector and the acceleration vector. Okay, so what's happening here? This object, this ball is thrown down towards the ground. So it starts out with a downward velocity and it goes straight down towards the ground. This graph would look different depending on what you choose as your zero position and your positive direction. Let's say that we choose our zero position to be at the ground and our positive direction to be up. Okay. So what would a position versus time graph look like for this motion? Well, we know we would start at some positive value because this is starting above the ground. And we know that we would start with a negative velocity because at the instant it's released, it's moving towards the ground. So I'm going to start with a negative slope. And then from there, it's going to be concave down because gravity accelerates this thing down, which with our choice of positive direction is negative. And so it looks something like this. Okay, so that's a position versus time graph of this motion. Now, what if instead we want to draw the path of this motion and at a single instant, the velocity and acceleration vectors? Okay, well, here's the ball, at whatever instant we've chosen. And the path goes something like this. Not something like that, exactly like that. It's just going to go, straight down. Okay, so what can we say about the velocity and the acceleration vector at this point? Well, the ball is moving down, so the velocity is going to be down. So there is the velocity vector. And what can we say about the acceleration vector? Well, it's accelerating down. Another way to think of it is that this ball is speeding up. And so if it's speeding up, the acceleration and the velocity have to be in the same direction. And we don't care about the magnitudes of these, only the direction. And so the acceleration is also straight down. If we did a different problem where this ball was thrown up into the air and it's on the way up, the velocity would be up. The acceleration would still be down because it's slowing down. And so these are the two ways of representing this one-dimensional motion. A path that you see here with a velocity and acceleration vector, and a position versus time graph. Okay, so now in 2D, how are we going to represent the motion in 2 dimensions? Well, there's not really going to be such a thing as a position versus time graph anymore. You could, so there's no P versus time graph anymore. You could graph the X position versus time and then the Y position versus time, but it's pretty cumbersome to deal with, so we're not going to do that. And so the only way we're going to represent this motion is to sketch the path of the motion. And that's going to be some kind of curve in 2 dimensions. And on top of that, we're going to represent the directions of the velocity and acceleration vectors. But now these are a little more complicated in 2D than they were in 1D also, because we don't just have speeding up and slowing down, we have turning also. Okay, so let's talk about the kind of vectors that we're going to see on this type of picture. So first is the velocity vector. What do we know about the velocity vector? Well, it's going to be tangent to the path. in the direction of the motion. Then the second kind of vector we're going to draw is the part of the acceleration that's parallel to the velocity. So I'm going to call this acceleration parallel. If the object is speeding up, then A parallel is the same direction as the velocity. If, on the other hand, the object's slowing down, then A parallel is going to be opposite the direction of the velocity. Okay, so notice that this is the only kind of acceleration that there is in a one-dimensional problem. Like if we look back at this example we just did, the velocity is tangent to the path, which is, in this case, in the direction, just along the path because it's a line. And it's speeding up. So we have this part of the acceleration that's parallel to the velocity, and it's in the same direction as the velocity. There's no other part of the acceleration in 1D, so this is all of the acceleration. In 2D, we're going to have to deal with this other part too. So now we also have to think about this part of the acceleration, if we're in 2D, that's perpendicular to the velocity vector. And so the direction of the part of the acceleration perpendicular to the velocity is the way that the object is turning. One way you can think about that is if the object wasn't turning at all, its path would stay exactly along the velocity vector. So whichever side of the velocity vector the path lies on, that's the direction that the object is turning. Now, based on these two parts of the acceleration, what can we say about the total acceleration? Well, it's equal to the sum of the parallel part of the acceleration and the perpendicular part. And this is why we did that exercise in lab 3, where we figured out all the possible directions that you could get by adding two vectors when you don't know their magnitude. Because we don't know the magnitude of the parallel part and the perpendicular part, we've just figured out the directions at this point. But the total acceleration is going to be anything in between those two directions. Okay, so let's see how this works in some example problems. And before I go into this, let me say one more thing. What if the object isn't speeding up, it's only turning? Okay. Well, if it isn't speeding up, then there's no A parallel, that's 0. And that means that the total acceleration is just going to be the direction of A perpendicular because you're not adding anything to it. An example of that we've seen in class is uniform circular motion. The object isn't changing speed, and so all you have is that centripetal acceleration. And what if, on the other hand, the object is changing speed, but it's not turning? Well, then that reduces back to a one-dimensional problem. The thing is just moving along a straight line, and so all of the acceleration is just parallel to the velocity. It's either in the same direction if it's speeding up, or it's in the opposite direction if it's slowing down. And if it's not changing speed and it's not turning, then both of these are 0, and you have 0 acceleration. That's a case of constant velocity, and so the acceleration is 0. Okay, so let's say that we have this car. We're looking at it from above. And let's say it's following a path like this. Okay, so it's going this way along the path. And at this instant right here, let's say that the object, the car, is slowing down. So what can we say about the acceleration direction of this car? Well, first, I'll draw the velocity vector, which is tangent to the path at this instant. So at this instant, it's going this way. Next, we know that at this instant, the car is slowing down. So the parallel part of the acceleration is opposite the velocity. Next, to figure out which way it's turning, look at where the path goes from this point, which side of the velocity vector. It's going to the right, and so I'm going to draw a vector that's perpendicular to the velocity that's to the right. These should, let me draw it a little more carefully, these should all be perpendicular to each other. A parallel and V need to be, parallel. And this perpendicular part needs to be perpendicular to both of those two. So there's a perpendicular. So now what do we know about the direction of the total acceleration? We can't say a direction for sure. We can't specify it completely because we don't know the magnitudes of these two. If we did, we could just use vector addition and come up with the perfect direction for the acceleration vector. But we just know we're adding a vector in the direction of A parallel to a vector in the direction of A perpendicular. And so what we know is that the total acceleration vector, I'll do it in black here, is in between those two somewhere. Okay. So we know that there's this 90-degree range of possible directions for the acceleration vector. Okay. Let me do another example where we have an object that's in projectile motion. So let's say that we have an object that's thrown and it follows a path like this. Okay. What can we say about the acceleration of this object? Let's say first when it's over here in its flight, and then second when it's over here in its flight. Okay. So in the part of the flight where it's on its way up, well, before I start analyzing it according to A parallel and A perpendicular, just from our study of projectile motion, do we know anything about the direction of the acceleration? Yeah, we already know that the total acceleration is down because the only thing acting on it, the only acceleration is a gravitational acceleration. So when I come up with my 90-degree range of possible directions for that acceleration, a downward vector better fall in that range in both of these cases, or else something isn't working. Okay, but we're going to see that it does fall in the range we come up with this new approach, this new way of thinking about it. Okay, so over on the left, the velocity vector is tangent to the path in the direction of motion, so it's this way. Now, is the object speeding up or slowing down? Something in projectile motion, if it's on the way up, is always slowing down. So there's a parallel part of the acceleration that's opposite the velocity. Now, is the object turning? Yeah, it's not following a straight line. That means it's turning. And so our perpendicular part of the acceleration is the way that it's turning, which is this way. So that's a perpendicular. And you can see that because the path falls on that side of the velocity vector. So what are the possible directions for the acceleration vector? It's in between a parallel and a perpendicular. And so it has to be somewhere in this range. And so what I said before was, well, we know the acceleration needs to fall in this range. And from our previous knowledge of projectile motion, we know the true acceleration is straight down. Does a downward vector fall in this range? Yes. So these two agree with each other in that sense. Okay, now what about the ball, the object, when it's on the way down over on the right side? Well, the velocity vector is tangent to the path. This time it's on the way down, so something in projectile motion is speeding up if it's on the way down. So a parallel is in the same direction as the velocity. Is it turning? Yes. Something in projectile motion, unless it's going straight up and straight down, it's always turning because of the influence of gravity. And it's turning this way in this case. So there's a perpendicular. And so the total acceleration is between a parallel and a perpendicular. So it falls somewhere in this range. So again, we know that the acceleration is down. Does the downward vector fall in this range of directions? Yes. So this new way of analyzing this problem is consistent with what we know about free fall. Okay, so that's really the idea of this lab. Please email me and I'd be happy to talk about it over Zoom if you have any questions.